In our last video, we observed some patterns that occurred when converting from the factored form to the standard form. We then used those patterns to help us convert from the standard form back into the factored form. With the factoring process, however, we kept one key item consistent. All of those quadratics had a leading coefficient of 1. So, what happens if we start using other leading coefficients? Well, let's try out a couple examples here and see what we can observe. Notice that, like before, we still need to do double distribution, and that process still results in terms that are quadratic, linear, and constant. However, when we get around to working our way backwards through this process, notice the challenges that those leading coefficients will introduce. For example, the standard form in both instances starts with 6x squared. But we don't know if that term was the result of 6x times x or 3x times 2x. So instead of just needing to guess at the constants in our factors, we'll also potentially need to guess at the coefficients of the linear terms. Also, notice that for the standard form, the linear coefficient is no longer just the sum of these two numbers. These issues will add an extra layer of complexity to the factoring process. So let's get to work on navigating that complexity and factor some more quadratics. Before we truly dive into the complexities of factoring quadratics with leading coefficients, let's look at a special situation that will be much easier to factor. Take this problem, for example. One way that we could approach the factoring process here is to write out the parentheses for our factors and start by filling in a 3x and an x, since we know that the product of those two terms will be 3x squared. Then, we could start making guesses at what the constant terms of our factors would be. While this approach would eventually lead us to the correct answer, there is a simpler way to go about this. Notice that all of our coefficients are divisible by 3, which means that we don't have to think of this as the result of double distribution. Instead, this is simply the result of regular distribution. For instance, consider this quadratic. If we multiplied this quadratic by 5, the distribution process would result in a new quadratic where all the coefficients are divisible by 5. That means that if we wanted to work our way backwards from here to here, we could simply divide each term by 5 and place the 5 outside a set of parentheses. What this means for our actual problem is that we can imagine this as being 3 times something. We just need to figure out what that something inside the parentheses should be. And to do that, we'll just divide each term by 3, which gets us x squared plus 7x plus 10 for the expression inside the parentheses. At this point, you might think that we're done since we factored out a 3, but unfortunately, this expression is only partially factored. It turns out that the quadratic inside the parentheses is still factorable, so we need to break that expression into 2 linear factors. Fortunately, though, this expression no longer has a leading coefficient, so we don't have to worry about any of the added complexities of factoring with a leading coefficient. Instead, we can follow the process that we've done many times before and achieve this result. With that, let's look at a few more examples of this process. And an important note to make about this process is that we always want to identify the largest number or expression that goes into each term. For example, we can quickly see that since each term here has an even coefficient, they're all divisible by 2, which would allow us to rewrite the quadratic this way. However, if we look back at our original expression, is there a number even larger than 2 that goes into each term? It turns out that there is. 3 also goes into each term, meaning that we could write things like this. But hold on. If 2 goes into the coefficient of each term, and 3 does as well, that means that 6 should also go into each coefficient. Thus, we can factor out a 6 which is in fact the largest number that we can factor out. We call this the greatest common factor, and this greatest common factor is what we'll initially look for whenever we have a leading coefficient. For our next problem, it looks like the greatest common factor is 2, which would allow us to rewrite the problem this way. And while factoring out a 2 is a valid way to simplify this problem, it turns out that 2 isn't actually the greatest common factor. Notice that since we don't have a constant term, our two remaining terms both have x's in them. And it turns out that the greatest common factor doesn't have to be just a number. It can also contain variables. Thus, since each term here is divisible by both 2 and x, our greatest common factor is 2x. Then, when we factor out that expression and determine what goes inside the parentheses, we can see that we only have a linear expression inside the parentheses, which means that we're done factoring. In our next example, you might not think that there's a greatest common factor at all. And in a sense, that would be correct. However, having a negative coefficient for our quadratic term can make things kind of annoying. So we're actually going to pretend that -1 is our greatest common factor, and proceed from there. When we do this, we have to divide each coefficient by -1, which essentially just flips the sign of each term. Then, we can further factor the expression inside the parentheses to get this result. And notice that instead of writing -1 outside the parentheses in our final answer, we just put a negative sign, since that has the same effect. For our final example, the greatest common factor turns out to be 3. And when we factor out a 3, we get this result. At this point, though, we run into a problem because we haven't factored this sort of expression yet. So for now, let's just leave the problem in this state with the knowledge that we'll eventually learn how to factor this further. It's now time for us to learn how to deal with leading coefficients other than 1 that can't be factored out as a greatest common factor. In fact, let's start with the expression that we were unable to factor in our last section, 2x squared plus 17x plus 30. We'll start this process by writing the parentheses for our linear factors. But instead of just placing an x in each factor, we have to put a bit more thought into the linear term of each factor. So we need to ask ourselves, how is it possible to get 2x squared as the quadratic term of our result? Thankfully, there's really only one option here, 2x times x. So let's put a 2x in one of our factors and an x in the other. Now, let's focus on the constant term of our desired result, which is 30. So as we've done before, let's list out pairs of numbers that multiply to 30. You might even notice something special about one of those pairs, which is that 2 and 15 add up to 17, the coefficient of our linear term. So let's make a guess at the constant terms of our factors by using 2 and 15. Next, we'll multiply things out to see if this is correct, and we'll eventually see that this is incorrect. This might come as a surprise to some of you, but if you think back to the introduction to this video, we did notice that leading coefficients in our factors threw off some of our patterns, including any patterns that we had observed about the linear coefficient of our result. This means that choosing the constants to include in our linear factors is going to be much trickier, and we can no longer just add up the constants to see which pair is correct. In fact, even the order in which we place the constants is going to matter. Check out what happens when we switch the order of the 2 and 15. We get a completely different linear term. And while that new linear term is much closer to what we wanted, it's still not correct. Essentially, what we need to do here is experiment with each pair of numbers that multiplies to 30. We'll try switching the order of the other pairs of numbers that we've tested, but when we see that they don't work either, we'll have to move on to our last option. So we'll try 5 and 6, and when we multiply that out, we actually get the correct linear coefficient. Thus, we've successfully factored this quadratic. But for the sake of completeness, let's check out the last option before moving on. Our next problem will follow some similar concepts, but this time we'll have some negative coefficients to deal with. We'll start by filling in a 3x and an x in our linear factors, since those will multiply to 3x squared. A slight difference here from what we've done before, though, is that we can't put plus or minus signs in our factors yet. We do know that one factor will contain a plus sign and the other will contain a minus sign, but we don't know which will be which. Instead, we'll list out the ways to reach -21 and start experimenting with those. As we begin that process, the number of options that we have to experiment with might feel a bit daunting. However, if we pay attention to some trends that are occurring, we should be able to move a bit faster. For example, when one of our factors has a constant term of -21, the result has a relatively large linear coefficient. And since our goal is to finish with a linear coefficient of -2, we can probably determine that using a 21 is out of the question. So let's save ourselves some time and skip this option for constants, since it also contains a 21. Next, we need to try 3 and -7. This combination can actually lead us to another observation that can help simplify this process in the future. Notice that the standard form for this expression has a greatest common factor of 3. This happened because the first linear factor also had a greatest common factor of 3. So before we even did the double distribution for this guess, we could have known that it was incorrect, since our original expression does not have a greatest common factor of 3. We do, however, need to try the combination with -7 and 3, but that ends up not being correct either. This leaves us with one final option, and we now know that the -3 can't go in the same factor as the 3x. So we'll put the 7 in the first factor and the -3 in the second factor. And once we do our double distribution, we can see that this ends up being the correct answer. Our next example will follow these same principles. So as we're going through our options for constant terms, we can eliminate some options before we even convert them to the standard form. Then, when we try out -2 and -10, that happens to be the correct answer. Thankfully, we didn't have to go through all of our options to find the final answer this time, and that's just how these problems will work. Sometimes we'll get lucky and find our answer quickly, and other times, the correct answer might be close to the last option that we guess. Now, up to this point in this section, we've looked at quadratics where the leading coefficient is prime. However, we can get yet another layer of complexity if our leading coefficient can be factored in multiple ways. For example, there are two ways that we could achieve this 8x squared. That could be the result of 8x times x, but it could also be the result of 4x times 2x. We'll pick one to start with, but then we need to jot down our options for how to achieve the constant term of our desired result. Now, 1 in 63 seems like an unlikely option, since the 63 would give us excessively large linear terms. However, we should probably try out 3 and 21 in both orders. Once we see that those are incorrect, we'll jump to 7 and 9, which happens to be correct. Thankfully, we found our correct answer before we had to try the 8x and x combination. That won't always be the case, though. In this problem, if we started with the 3x and 2x combination, we would have to go through 24 combinations of constant terms just to realize that none of them are correct. Sure, we could eliminate many of them quickly thanks to greatest common factor issues, but it would be pretty tiresome nonetheless. Then, we would have to move on to 6x and x and keep searching until we found this result. While there are many other examples that we could do to solidify our skills with factoring, let's instead spend a bit of time discussing the limitations of factoring. Suppose we had this problem. Our approach here would once again be to list out the combinations of linear terms that could multiply to 16x squared, along with the negative constants that could multiply to 45. Then, after meticulously testing 15 combinations of these puzzle pieces, we would realize that none of them work. It turns out that this expression is not factorable, but going through such a lengthy process to discover this would be pretty disheartening. Or take this problem. Since it has a leading coefficient of 1, we can list out pairs of numbers that multiply to -20 and see what pair adds up to 4. Unfortunately though, none of our pairs add up to the linear coefficient, so we can once again say that this is not factorable. There is, however, something different about this situation. Notice that in our list of sums, the results were increasing as we moved down the list. And at this point, the result jumped from 1 to 8, while skipping over the 4 that we were hoping for. But what if this is actually factorable, and we just need to try out numbers that aren't integers? This is an interesting idea, and if we tried out some decimals, we would see that it is actually possible to get closer to 4. Still, picking exactly the right decimal would be challenging to say the least. It turns out that this expression is technically factorable, and the factored form would look like this. But since the square root of 6 is irrational, it turns out that we never would have guessed the correct decimal, since the actual answer is a decimal that goes on forever. Due to the wide variety of situations that can arise with quadratics, factoring will often not be the best option for analyzing any given quadratic. Sure, if we have integer coefficients and can find a factored form relatively quickly, then factoring is probably worth it. But don't expect factoring to work every time. Still, in the situations where it does work, factoring can be a powerful tool for analyzing, manipulating, and simplifying quadratics. That concludes part 2 of this video on converting quadratic expressions into the factored form. Hope you learned something new, and thanks for watching.